Good evening friends. In today's lecture, we will be discussing about three-phase system. In our previous lectures, we have covered all about single-phase systems, series resonance, parallel AC circuits, and other related areas. From this lecture onwards, we will be discussing about three-phase system. Three-phase system is otherwise written as three-phase system with the symbol of phi representing the number of phases. This lecture is basically focused on the introduction of three-phase system and its following attributes. So before we begin with three-phase system, one has to understand the difference between a single-phase system and a polyphase system. As we have studied in our previous lectures, a single-phase system has a single-phase voltage and a single-phase current. Now coming to the polyphase system, the word poly refers to multiple. So for a polyphase system, there shall be multiple phase voltages and multiple phase currents. Why is a single-phase system being called as a single phase? Let us go back to the basics of generation concept. A generator setup looks something like this. This represents the electromagnet and there is a coil being placed in this electromagnet. Now when this coil is made to move within this electromagnetic field, a current is being produced according to Faraday's laws of electromagnetic induction, or the voltage that is being produced by this type of setup is a single phase system. If we are talking of polyphase system, then we should have a set of electromagnets, or you can say we can have this set of electromagnet as well, and within this set of electromagnets we can have n number of coils placed within. So if there are two coils placed within this electromagnetic set for the generation of electricity, then it will be called as a two-phase system. If three coils are placed within this electromagnetic set, then it would be called as three-phase system. If there are 6 coils or 6 windings being present, then it will be called as a six-phase system, and so on. So a single-phase system is basically called as a single-phase system because of the presence of single winding that is used in generation. Whereas for a polyphase system, there shall be multiple windings present. Now we have studied all about the single-phase system. So for a single-phase system, as there is a presence of a single winding, how is the supply being represented? Usually in these single phases or multiple phases, we will be having the voltage as the supply. So how is that voltage being represented for a single-phase system? Now we are all aware of one thing, that there are primarily two ways of representing the supply or representing this voltage. One is by the sinusoid and another way is by phasors. The essence is both these representations are interrelated to one another. Sinusoid represents the sinusoidal equation of the voltage, whereas the phasor is the complex representation of this sinusoid. So for a single phase system, the supply is being represented something in this manner, where this capital Vm represents the peak magnitude of the voltage that is being generated, and this is the waveform of the signal that is being generated. Sine is the most widely used waveform. Sine or cosine both can be used. Now coming to this polyphase system, there will be multiple voltages being generated. In such a scenario, how are we going to represent the voltages? Let us consider a three-phase system, since we are going to study in detail about this system. For a three-phase system, we will have the generation of three sets of voltages. It will be V1, V2 and V3. Now the question is, how will these three different voltages be represented? Again, we will be representing all these sets of voltages using sinusoids. But what will happen to their peak value? What will happen to their frequency value? Now this is how a three-phase voltage is being generated that we have discussed few minutes earlier. So under a particular set of electromagnet being used, placing three windings within this structure, when these windings are made to rotate, a three-phase voltage is being generated. Now since the number of windings are placed within a set of this electromagnet and they are being made to rotate at a particular frequency, so the values of the voltages that will be generated for a three-phase system, or for the matter of fact any number of phase of system, the peak value of the voltage and the frequency, these two parameters would remain same for a polyphase system. I am repeating this part once again. For a polyphase system, there will be multiple voltages along with multiple currents. So the question is, what happens to the peak values of each voltage? Since they are being generated under the same set of electromagnets, by placing the required number of windings, the peak value and the frequency of a polyphase system remains the same. So how are we going to express the three phases that will be generated for a three-phase system? So V1 will be Vm1 sine omega t. V2 will be Vm1 sine omega t. V3 will be Vm1 sine omega t. Or is there any difference between these three voltages that are being generated? We could see none, since the peak magnitude and the angular frequency, which is based on the frequency of the system, they are both same. Then how to distinguish between these three voltages? In order to distinguish between these three voltages, there is another parameter which comes into the picture. And what is that parameter? It is called as the phase. That's how the name is a three-phase system. In spite of the peak magnitudes same, in spite of the angular frequency being same, the phases of the voltages that will be generated will be different for a polyphase system. Since in a three-phase system there will be three sets of voltages that will be generated, each voltage value will carry a different phase value. Let us see what are the values of these phases. The value of the phase is determined using a formula, and that formula is given as phi or theta is equal to 360 degrees upon n, where n represents the number of phases. This expression is valid for any number of phases except n is equal to 2. For n equals to 2, this expression is not valid. That we will see later on. Right now, let us use this expression and check out how the three voltages for a three-phase system is being represented using this formula. Now for a three-phase system, the value of n will come out to be 3. So what will be this value of phi? This phi will come out to be 120 degrees for the value of n to be equal to 3. So now, when you already know what is the value of phi, how will be the three sets of voltages being represented? V1 can be written as Vm. Instead of Vm1, I am writing it as Vm, since all the peak value magnitudes are going to remain the same. Vm sine omega t plus 0 degree. The first signal always starts with the 0 reference, or the first signal is always considered as the reference signal. What about the second signal? Since the theta is at 120 degrees, so after 120 degrees, the second signal or the second supply value will be generated. So it will be given as Vm sine omega t. Now what should I be writing over here? Will it be plus or minus? Please remember one thing. The signal 1, that is V1, is generated first, and the signal 2, that is V2, is generated after the generation of the first signal, which clearly means that the value of V2 is lagging V1. By what angle? By 120 degree. Since it's a lag, it will be represented by minus 120 degrees. Now, for a three-phase system, you will have three values of voltage. Now, coming to the third value, one will have Vm sine omega t. Now, what will be the phase difference? I cannot write over here minus 120 once again. Why is it so? Because the signal V3 will lag V2 by 120 degree. Already the signal V2 is lagging the reference by 120 degree. So if I write here V3 as Vm sin omega t minus 120 degree, then signals V2 and V3 would be similar. But that is not the case. Three-phase system means there are three individual signals being generated or three individual waveforms being generated. Since the signal V3 is generated after a phase difference of 120 degree with respect to V2, it will be written as minus 240 degrees. So finally, we obtained the three sets of values that are being generated for a three-phase system. Now let us see, if we are representing these three signals in a waveform, how do they look like? Now let us first draw the first signal. The first signal is given as Vm sin omega t. So it is a normal sinusoidal waveform with a phase difference of 0. So how can it be drawn? So this is a sinusoidal waveform with reference 0. Now this is where the 90 degree of the waveform takes place. This is where it is 60, this is where it is 30, this is 90 plus 30 and this is 90 plus 60. So a simple half wave of a sinusoidal waveform can be divided into 5 points comprising of 30 degrees each. Why did I do like this? It is because I have to draw the second waveform and the second waveform has to start from 120 degrees of the first signal. So where do we get the 120 degrees of the first signal? Now as I had said, divide this sinusoidal half waveform into 5 points. The midpoint represents 90 degree and each point is at a point of 30 degrees. So 90 plus 30 represents this point. So again, let us draw first 5 points. Now I am taking this as 90 degree and this are in the points of 30 degree each. So starting from here, where do I get all the 5 points? I get all the 5 points up till here. So can I draw a half circle here? Now let me proceed ahead. Now this I have represented the second waveform. Now coming to the third waveform. The third waveform starts at minus 240 degrees of the first waveform, or with respect to the second waveform, it should be minus 120 degree of the second waveform. Now this is the second waveform as you can see. Now this is the 120 degrees of the second waveform and which is coming out to be minus 240 degrees of the first waveform. So the third waveform starts from here. Now I have drawn the third waveform as well. Let me mark it. This is the first waveform. This represents the second waveform and this is the third waveform. And as we can see, all the three are having the same peak magnitude and the angular frequency for all the three waveforms are same. This is how three different signals are being generated from a three-phase system. The signals are not different in terms of their peak magnitude or frequency. They are only different in the manner or in the phase at which they are being generated. Now there is something else that we also need to know. This is the third waveform. Now the waveform starts from here and all these waveforms will go around in a cyclic manner. After the generation of this V3, once again V1 will be generated, followed by V2, followed by V3. So at any instant of time, if we check the waveform, then it might look like this. What have I done here? I have extended this third waveform towards the negative half of the x-axis. Or once the generator starts generating these waveforms at a particular instant of time, this is the order which they maintain. What is the order? V1, V2, V3, V1, V2, V3. So if I capture a particular moment during the generation, let's say something like this. So we can see there is a time when V3 can appear prior to that of V1 because everything is going in a cyclic manner. Similarly, V2 appears ahead of V3, which you have already studied. So I have represented this occurrence of V3 prior to V1 at some instant of time on this negative x-axis. Now we can see over here that this is the place from where the reference or the first signal is being generated. However, the third signal is getting generated prior to it. This is for a particular instant, not at the beginning of the generation. Hence, this V3 can also be written as Vm sine omega t plus 120 degrees. Why plus 120 degrees? Because we have divided each point into 30 degrees. Since this is the starting of V1, we have 30, 60, 90 and 120 degrees. 120 degree ahead, V3 is seen to be present for a particular instant of time when they are being generated. Hence, we can write down finally the complete set of representation of the three phases for a three-phase system. V1 is written as Vm sine omega t. V2 can be written as Vm sine omega t minus 120 degree. V3 can be written as Vm sine omega t minus 240 degrees or Vm sine omega t plus 120 degrees. So this is the complete set of representation of the three-phase systems or of the three phases that are being generated in a three-phase system. So this is the sinusoidal representation. Very soon we will be studying about their phasor representation as well. I hope this part is clear and you also know why the voltage V2 is carrying a negative sign, because it is generated after the generation of V1, and V3 is carrying minus 240 degree because it is generated after the generation of V2, and it is carrying this reference of minus 240 degree as a reference with respect to V1. And why is it also represented as plus? Because when these signals are being generated, they will be generated continuously. So at a particular instant of time, this V3 can be seen or has been seen to be ahead of V1 by 120 degrees. Hence, V3 can be represented in these two manners. Prior to this phasor representation of the sinusoids, we have to discuss one more thing, that why that expression of theta, which is 360 degree upon n, is not valid for n equals to 2. Let us check that. We'll try to prove this using the waveform concept, and let us assume that this expression is also valid for n equals to 2. In that case, what will be the value of theta? It will come out to be 180 degrees. So for two phases, we will have two values of voltages. V1 will be given as Vm sine omega t plus 0 degree, because that would be the reference. And what will be the value of V2? It will be Vm sine omega t minus. You know why it is minus? Because this signal is generated after the generation of V1. And by how many degrees? It is minus 180 degrees. Now let us plot these two waveforms or these two signals on the sinusoidal scale. Let me first draw V1. So this is how V1 can be represented. It is a pure sinusoidal curve with a reference at 0. Over here, I am not breaking this half waveform into 5 points because the second signal starts at 180 degrees. And this is the point where the half wave signal ends the positive half wave signal ends and the negative half cycle starts. So from this point onwards, the second signal will start. So let us now represent the second signal as well. So I represented the second signal as well. So in this manner, we keep on representing the first signal as well as second signal and so on. So what do we infer from here? If we go by that expression of 360 upon n, and if we obtain an angle of 180 degrees, then after the generation of the signal V2, one can see that the positive half cycle is in complete negation with the negative half cycle. And so on, the signal continues. So what is the final output? The output of the system is just a half wave signal which is produced because of the half wave cycle of V1 only, beyond which the signal is completely dropping down to 0. Hence, a two-phase system won't work if theta is equal to 180 degrees. That is why this expression is not valid for a two-phase system. Rather, for a two-phase system, the value of theta is taken as 90 degrees. Now let us see what happens if we are taking a value of phase difference as 90 degrees. First, we will see how the values of voltages are being represented. V1 can be written as Vm sin omega t plus 0, of course, because that is the reference, and V2 will be written as Vm sin omega t minus 90 degrees. Let us represent these two signals in the form of their waveforms. This is how V1 would be represented. Now, this V2 would not start at phi equals to 180 degree. Rather, it would start at phi equals to 90 degree, which is this point. So let me represent V2. This is how V2 would be represented, and so on. Now from here, we can see that the value of the signal or the value of the resultant signal is not dropping down to 0 at any instant of time. Hence, this is a feasible system for which the theta value is equal to 90 degree. That's the reason as to why for a two-phase system, the value of theta is taken as 90 degree and not equal to 180 degree that we will be obtaining from the expression. So I hope this part is clear, that why we are not taking that expression for n equals to 2. Let us now move to the phasor representation of the signals that was being obtained for a three-phase system. For a single-phase system, the sinusoid could be represented as Vn sin omega t. What is a phasor representation? Capital V1 is equal to Vm angle 0 degrees. Phasor is the complex representation of the sinusoid. Now for a three-phase system, we have three values of voltages. So these are the sets of voltages that were being generated. What will be the phasor representation of these voltages? The first one would be Vm angle 0 degree. The second one would be represented as Vm angle minus 120 degree. All the waveforms are in the sinusoidal representations. So there is no requirement of changing the reference to cosine or sine. We can directly take sine as the reference and we can obtain the phasor from the corresponding sinusoidals. And the last one would be given as Vm angle minus 240 degree. I'll be considering only minus 240 degree over here. But one has to remember that this minus 140 can also be written as 120 degree. Now let us represent the phasor diagrams. For a single phase, how was the phasor diagram being represented? This is V1, which is Vm angle 0 degree. Now for a three-phase system, since there are three values of voltages, we will have all the three phasors present on a single diagram. Now let us represent our reference first. This is V1, which is Vm angle 0. What about V2? V2 is Vm angle minus 120 degree. Minus means we have to travel in the clockwise direction. I'm writing it over here. Negative angle means it's a clockwise rotation. Positive angle means it is a anti-clockwise rotation or counterclockwise rotation. So since it is minus 120, this is how V2 would be represented. And this in the clockwise direction represents minus 120 degrees. What about the third waveform? It is at an angle of minus 240 degree or at minus 120 degree lagging behind V2. So this is where we will be representing V3. This angle is minus 120 degree. Together this value is minus 240 degree. Now we have already studied one thing as well, that V3 is ahead of V1 by plus 120 degree. That means there should be an anti-clockwise rotation as well. Now if we are moving in the anti-clockwise direction like this, so this is plus 120 degrees. So this is how the voltages are being represented in a phasor diagram, with V1 as the reference, V2 lagging V1 by 120 degree, V3 lagging V2 by 120 degree or lagging V1 by 240 degree or leading V1 by 120 degree. So these are the phasor representations for a single phase as well as for a three-phase system. Now let us study the advantages of this three-phase system over the single-phase system. Why are we in a dire need of using this three-phase system over the single-phase system? There are a few points that one has to take care of. The first point is the output of a three-phase system is greater than that of a single-phase system. The second point being, for a single-phase system, the instantaneous power is fluctuating in nature. By instantaneous power, one means the product of the sinusoid of the voltage multiplied with the sinusoid of that of the current. That power obtained for a single-phase system is fluctuating in nature. However, for a three-phase system, that power, that instantaneous power, and how will we obtain the instantaneous power for a three-phase system? Since there are three values of voltages involved, we have to multiply the respective currents obtained with their corresponding voltages and add them up together. That is V1 instantaneous into I1 instantaneous plus V2 instantaneous into I2 instantaneous plus V3 instantaneous into I3 instantaneous for a three-phase system is a constant. And the last point is, if we have a three-phase system and we require a single-phase system or a two-phase system, then that can be easily taken out from a three-phase system. Whereas the reverse is a complex task to do. So what can we write? When single-phase or two-phase inputs are needed, it can be taken from a three-phase system. So these are the three basic advantages of a three-phase system over a single-phase system. And due to these three basic, or you can say unique advantages of three-phase systems over the single-phase systems, these phase systems are being widely used all over the world. Now since we are studying about the three-phase system, then one must be aware of a very important term used in three-phase system, that is called as phase sequence. Phase sequence is the sequence in which the voltages in the three-phase reach their peak value. So from the sinusoidal representation, we had already seen that V1 reaches the peak value first, followed by V2, followed by V3. So this is the sequence in which these voltages reach their peak value, and this is called as phase sequence. Now these phase sequence are of two types. One is positive phase sequence, another one is negative phase sequence. So for that, let me first draw the phasor diagram once again. The phasor diagram is represented as this: V1, V2, V3 all same in magnitude, and they are separated by an angle of 120 degrees each. Now these voltages or these phases have been given a particular name. The reference voltage or the first voltage that we begin with is called as R, representing red. The second one is given as Y, representing yellow. The third one is B, representing blue. So if R is generated first, followed by Y, followed by B, then the sequence is called as R, Y, B. And this sequence is called as a positive sequence. And the sequence does not end here. The sequence is continuous in nature, which is RYB, RYB, RYB and so on. And this sequence, the way we are traveling RYB, RYB, it is called as a positive sequence. If this is called as positive sequence, then what will be the negative sequence? If we change the order in which the voltages reach their peak values. So it is always R which will reach the peak value first. So the sequence will start with R. But instead of the yellow or Y being the second phase which reaches its maximum value next, in the negative sequence it will be the blue or B which reaches its maximum peak first. So the sequence will be R, B, Y, R, B, Y and so on. This sequence is called as a negative sequence and this sequence is called as a positive sequence. Positive sequence means R, Y, B. Negative sequence means R, B, Y. Now you can see that in one sequence we are traversing in the clockwise direction and in another sequence we are traversing in the anti-clockwise direction. So this traversing has something to do with the rotation of the machine. If the machine is rotating in the anti-clockwise direction, then it will generate a positive sequence. And likewise, if the machine is rotating in the clockwise direction, then it will generate a negative sequence. Positive sequence is the most widely used sequence. There is another way also in which you can remember this positive and negative sequence. Till now we have always remembered that if there is a positive lead or a positive direction, it goes in the anti-clockwise direction. And if there is a lag, it always traverses in a negative angle and that happens because of the clockwise direction. Now this analogy is being used for the machine rotation as well. If the machine is rotating in the anti-clockwise direction, it will generate a positive sequence. If the machine is rotating in the clockwise direction, it will generate a negative sequence. Next we will study about the representation of these three phases. As there are three phases involved, which clearly means there are three windings present. So they can be represented as this. Each winding can represent a single phase. Since there are three phases, there will be three windings connected to their respective loads. So we can see over here, there are three windings present and each comprises of single phase. Now this part, the left part where the winding is present, is the source part, and the right part, which is represented by a box, which we have studied in our previous class, is being represented by the impedance or called as a load. So this is the source and the load. Now look at this part. This is a wire. Similarly, this is a wire. So there are two wires connected to each load. There are three loads. So there are 6 wires or there are 6 connections for a three-phase system. Now if we are using 6 connections together to make a three-phase system, it becomes very expensive and it makes the system complicated. So how to avoid this expensiveness and the complications of these 6 connections? In order to avoid these complications, the representation of a three-phase system is done in two ways. One is called as a star connection, the other one is called as a delta connection. The star connection is a Y connection. The Y can be represented as this or it can be represented as this. Whereas a delta is represented with a triangular shape, it is otherwise called as a mesh connection. Using the star or delta connection, one is able to reduce the 6 connections into 3, thus saving a lot of wires or a lot of conductors. Now let us see how we can make star connection out of these 3 phases and how will we make a delta connection out of these 3 phases. prior to making the star and the delta connection, there is one more thing that you should know. We have two paths present over here. One is the source part, one is the load part. Since there is a three-phase system, we will have three phases for the source. We will also have three phases for the load. This is a very important point one must remember. Now we will first make the star connection and delta connection for the source side. Then we shall make the star and delta connection for the load side. In order to study these two connections, I am making two columns. Let me first draw all the three sources connection over here once again. I have drawn all the sources. I have removed the loads for time being. Once we understand how the sources are being represented or are being connected in star or delta manner, the same technique can be used for the loads as well. The sources are being named as A1, A2 for the first phase, B1, B2 for the second phase, C1, C2 for the third phase. Now how do you make a star connection out of these three phases and six connections? In order to make the star connection, if A2, B2 and C2 are joined together, then one gets a star connection. Or if similar ends are joined together. What do you mean by the similar points? Now for a given phase, this side, the top part, is represented by all subscripts of 1, whereas the bottom parts are represented by subscripts of 2. By similar ends means all subscripts of 2 are being joined together. One will obtain a star connection. Let us see how the star connection would look like. This is how a star connection would look like. You have to keep that 120 degrees in mind while connecting a star connection for a three-phase system. So you can see here, this is the first phase, 120 degrees apart is the second phase. Again minus 120 degrees apart, we have got the third phase. Now let us move on to the delta connection. How would we get a delta connection? We have already joined the similar ends. Now that technique won't work. Now there is another technique which we can use. Can we join the subscript 2's with the subscript 1's? Like, can we join A2B1, B2C1 and C2A1 together? That can be called as dissimilar joints are being joined together, or dissimilar ends are joined together. When dissimilar ends are joined together, one gets a delta connection. Now let us see how the delta connection would look like. This is how the delta connection would look like. This one being A1, A2, B1, B2, C1, C2. Once again, see this. This is phase 1, 120 degrees apart. You are having the second phase. Again 120 degrees apart, you are having the third phase. Students, while marking this star and delta connection, one has to be very vigilant about the notations that are being used. Please make sure that your R, Y and B are 120 degrees apart from one another. And the manner in which A1, A2, B1, B2 and C1, C2 are represented for a star and a delta connection, these things are to be taken care of. So this is how a star or a delta connection is being made. Now this is made for a source. The similar thing can be done for a load as well. And how will it look like? Now this is the load representation for a star connection. And this is the load representation for a delta connection. There is one point that one has to take care of. When you are using the three-phase load or three-phase source individually, the terminals should be taken out in the right-hand direction. Now what is the problem if you take out the terminals in the left-hand direction? Now let me take this delta connection as a reference. Now this is R, this is Y and this is B. Now this is our basic notation that we have been following, because we are always going to use the positive sequence, the positive phase sequence R, Y, B. So this is R, Y and B. Now if you take out your terminals along the left hand side, it often happens that students make a mistake. They will consider this as the first phase, this as the second and this one as the third, which means they will be considering RBY sequence, negative sequence, which is incorrect. We are not going to use the negative phase sequence for our study. We will be only using the positive phase sequence. So you must remember to take out your terminals on the right hand side when you are using the loads or the sources individually. When you are considering them together, one has to be on the right, another one is to be there on the left. That I'll be teaching you in the next slide. But when you are considering them individually, please take out on the right hand side only. You must not consider the negative phase sequence. You must always consider RYB phase sequence. Now what will be these impedance values? It will be ZR, ZY, ZB. Similarly, this will be ZR, ZY and ZB. If the value of ZR, ZY and ZB are same, then such a load is called as a balanced load. Else, if these are not equal to one another, it is called as unbalanced load. We will be only considering the balanced load in our study as of now. We are not going to discuss unbalanced load in this lecture. Now let us go to the previous slides. In the previous slide, these windings represent the sources. This is VR, this is VY and this is VB. Similar we can write here. Or for a system, when sources have VR equals to VI equals to VB, that system is called as a balanced system. So we will be considering a balanced system having balanced load for our study for time being. So far we have studied the star connection and the delta connection representation for the sources as well as for the loads. Now when we connect the source to the load, we will have the whole picture. Now since there are two sets of representation, we will obtain four sets of connection for sources and loads when clubbed together. What will be those connection? The source can be a star connection, the load can be a star connection. The source can be star, the load can be delta. The source can be delta, the load can be star. Both the source and both the loads can be delta delta. Now I'll draw all of these figures combined together. Now over here I have drawn a star source and a star load. Now look here, I have joined the R phase to R phase. Now this is my Y phase and this is the Y phase of the source. They must be joined together. So I am joining Y to Y. And the last one is the B phase. This is B of the source, this is B of the load, and this is joined together. So this is a star-star source load connection. Likewise, I'll be drawing the star-delta connection. So here I have drawn the source as star and the load as delta. This is R, this is Y, this is B. For the load, this is R, this is Y, and this is B. Connecting R to R, connecting Y to Y, connecting B to B. Moving on to the next one. Now this is a delta connection of the source, this is the star connection of the load. This is R, this is Y, this is B. Likewise, this is RYB, connecting R to R, connecting Y to Y, connecting B to B. Moving on to the last part, that is delta source with delta load connection. I am representing the IY, RYB terminals, connecting R to R, connecting Y to Y, connecting B to B. So these are the four sets of representation of star delta with load and the source connection. You do not have any other connection apart from that. Since you have got two types of connection, you will have two types of sources. You can see here, sources can be either star or it can be either delta. So with the source star, you will have again two types of connection. One with the star load, one with the delta load, and with the delta source you can have a star load and a delta load. Now in your exam, mostly the connection of the loads will be given to you, whether the loads are in star or in delta. As long as there is no mentioning of the source connection in the question, you should not bring the source into the picture. I am repeating this part again. If in the question, if the source connection is not specified, then one need not bothered. If the source connection is specified in the question, then one should be looking for either of these four structures. Normally, the questions would be asked based on the load connections only. But there could be some questions, like you might get a practice set having questions where the source connection might be present as well. In that case, you have to look for the source connection as well. So with this, the basics of three-phase are done. Now we shall study in detail about this star and the delta connection. What are their features and what are their parameters and how are we going to work with them. So let us note down few differences between this star and this delta connection. So let us first draw a representation of a star connection. Because this is a generalized star connection, it could be either representing a source or a load. And this is how a delta connection looks like. So coming to the first point. Now for a star connection, there is an additional point, this point. And this point is called as the star point, neutral point, floating point, or the 0 point. However, there is no such point present for a delta connection. So we would write that there is no neutral present. Now what is the advantage of having a neutral in a connection? If there is an imbalance of currents in the circuit or in the phases, then this neutral provides a path for that unbalanced current to move out of the circuit. So one can write that the excess current can flow out of the circuit through the neutral point. As there is no neutral point present, what happens if there is an unbalancing being created due to the currents? There is no way the excess current can flow out of the circuit. Eventually, for a delta connection, it leads to the generation of harmonics. Now coming to the star connection, since there is a point which allows the excess current to flow out of the circuit, thereby maintaining the balance of the circuit, we can see here that the KCL can be applied over here. Likewise, for a delta circuit, KVL can be applied. Because of this advantage provided by this neutral point, this type of connection is widely used in residential sector. And because of the absence of this neutral point, this type of connection has got limited applications in the residential domain. So this is the basic difference between a star and a delta connection.